Hello my dear students, welcome back to my channel. Today with this video, we will cover all important points and formulas of chapter 2, that is electrostatic potential and capacitance, within 15 to 20 minutes. So different topics to be covered in this chapter are: first, electrostatic potential and potential difference, equipotential surface, relation between electric field and potential, electrostatic potential is a system of two charges and affected dipole electric field, conductors, insulators, dielectric and polarization, capacitor and capacitance, combination of capacitor series and parallel, capacitance of a parallel plate capacitor with and without dielectric between the plates, energy stored in a capacitor. So let us start first this topic with electrostatic potential and potential difference. First, electrostatic potential difference, then we will define electric potential. You know, if there is a charge, then around that charge electric field is present. If any other small test charge enters in that electric field, it experiences some repulsive force in this direction right now. So if you want to move this test charge from one point to another point, you have to do some work. That is nothing but electrostatic potential difference. Amount of work done in bringing a unit positive test charge from one point to another point in an electric field against this electrostatic force. So you have to move this test charge from A to B. So at point B, potential is higher. So VV minus VA equal to work done in moving a charge from A to B divided by Q naught. This is potential difference. Electrostatic potential is nothing but, if assume that one test charge is kept at infinity. So how much work, at infinity there is no electric field right now. So at this one, potential is 0. So how much amount of work done in bringing this test charge from this infinity to a particular point where you have to find the potential due to this charge Q. So that amount of work done in moving a unit positive test charge from infinity to a given point in an electric field is called electrostatic potential, from infinity to point P divided by Q naught. This is electrostatic potential at point P. Unit of both electrostatic potential and potential difference is volt. And how you define 1 volt? Potential difference between 2 points is 1 volt if 1 joule of work is done in moving a positive charge of 1 coulomb from one point to another point. And you know, it's 1 volt is how much? 1 joule per coulomb. And this is equal to 1 Newton per coulomb meter. What is its dimension? Its dimensional formula is m L square T minus 3 and A minus 1. This is dimensional formula of electrostatic potential difference, right? Next, now potential due to a point charge. You know, suppose there is some source charge Q, and due to this source charge, electric field exists around it. Now, what is the value of electric potential at point P at a distance r from this source charge? So, you know how to find. So first, you assume that there must be a test charge at this point and how much work required to move this test charge from A to B. Then you integrate for total work done from infinity to this point P. In this way, you find total potential. And its formula is given by V equal to 1 by 4 pi epsilon Q by R. You can write also K Q by R. This is the potential due to a point charge Q at a distance R from this charge. Now you know potential is a scalar quantity. So electric potential due to a system of charges. If there are large number of charges present in the system, then total potential at any point is equal to sum of potential due to individual charges. You can write in this way: 1 by 4 pi epsilon summation of Qi by Ri I equal to 1 to n. This is total potential due to a system of charges. After this, next, electric potential due to a dipole. You know, in dipole, what is dipole? It's system of two equal opposite charges. There is one axial position, there is one equatorial position. Axial position along the axis of the electric dipole. Suppose you have to find electric potential at this point P. Now, how you find? Suppose R is the distance from the midpoint of this dipole to the point P where you have to find electric potential. And 2A is dipole length. It means distance between plus and minus Q charge. So total potential along axial position is given by 1 by 4 pi epsilon P by R square, where P is dipole moment and P is given by Q into 2A. You can also write in this way: V equal to K P by R. K is 1 by 4 pi epsilon naught. Now next, along equatorial position. Along equatorial position, this is perpendicular bisector of the dipole. At point P, you have to find electric potential distance r from the midpoint of this dipole, right? So total potential along equatorial position is always 0. You must remember this point. Now, electric potential at any general point. Suppose this is the dipole minus Q1 plus Q. You have to find potential at this point P. And you know direction of dipole moment is what? From negative to positive charge. So this is the direction of dipole moment. Suppose you have to find electric potential at this point P, which makes angle theta with the dipole moment, right? And suppose the distance r from this point. Okay, so you have to find general expression for electric potential any point at a which makes an angle theta with the dipole moment. General equation is given by V equal to 1 by 4 pi epsilon naught P dot R by R cube, or you can write 1 by 4 pi epsilon naught P cos theta by R square, or you can write K P cos theta by R square. If theta is 0, you get along axial position. It means Kp by R square, this one, right now. And if theta is 90 degree, then this V equal to 0 along equatorial position. So this is a general expression for electric potential at any point which makes angle theta with the dipole moment at a distance r from this point. Okay. Next, relation between electric field and electric potential. Suppose there is a source charge plus Q. Now you have to find what is relation between E and V. So you know that due to this charge there is electric field around it, and if there is a test charge Q naught at this point A, it experiences force in this direction, right now. So if you want to move this test charge from A to B, you have to do some work. And how much work? In moving a distance of this test charge Q naught from A to B at a distance small dr. So small amount of work done is F dot dr, and F is in this direction and dr is in this direction. Both are in opposite direction. There is an angle 180 degree between these two. So it becomes minus F dr, and F is what? Force is equal to E into test charge Q naught. So dW equal to minus Q naught E dr, equation of number 1. By definition, you know what is potential difference between A and B? dW by Q naught equal to VB minus VN. You can write this difference as dV. So from here dW equal to minus Q naught dV. Now from 1 and 2, this dV equal to minus E dr, or E equal to minus dV by dr. This is very important formula. To remember this one. E is negative of potential gradient. If potential changes with distance, so you can say potential gradient minus dV by dr. And this negative sign shows that potential decreases in the direction of electric field. If electric field is in this direction, then in this direction potential decreases. At this point, potential is greater than at point A, because potential decreases in the direction of electric field. So hope you understood very well. Next is equipotential surface. Any surface that has same potential at every point on it. These are called equipotential surface. Suppose there is a positive source charge Q here. Now due to this positive charge, field lines are radially outward. And if you at a distance, equal distance from this source charge, field is same. So if you join these points, you get one sphere. So equipotential surface due to this positive source charge is a spherical shell. Due to negative charge also a spherical, concentric spherical shells, but electric field lines are radially inward. Now, there are some properties of equipotential surface. The electric field is always perpendicular normal to an equipotential surface. Suppose this is a positive source charge Q, and due to this source charge Q, equipotential surface are this one, right? So, electric field is always normal to this equipotential surface. Second one is two equipotential surface can never intersect. Why? Because at the point of intersection, there will be two values of potential, which is not possible. Then the direction of equipotential surface is from higher potential to always lower potential. No work is done in moving a test charge over an equipotential surface. If you want to move a test charge over an equipotential surface, no work is done. Why? Because at every point potential is same. If potential is same, then work done is what? Q into potential difference delta V. If potential difference is 0, because potential is same, work done is also 0. Last property, equipotential surfaces are close together in the region of a strong electric field. You know, near the charge, electric field is strong. So, these equipotential surfaces are very close to each other. Away from this charge, electric field is weak. So, equipotential surfaces are far away from each other. After this, you have to draw equipotential surface for different combination. For positive charge, equipotential surface is concentric spherical shells. Only field lines are radially outward. For negative charge, equipotential surface are again concentric spherical shells, but electric field lines are radially inward. For uniform electric field, equipotential surfaces are like this one, plane surface. Equipotential surface of two identical positive charges. For this one, suppose there are two positive plus Q and minus Q. Now due to this plus Q and minus Q, field lines are like this one, right now? Away from this positive, these are repulsive in nature. So electric field lines are this one. Now near this side, field lines are very close to each other. So equipotential, it means there is strong field lines. Left side, again this side also there is a strong field lines. Okay now. So this side equipotential surface are very close to each other, and this side equipotential surface are very far away from each other. So these are due to two identical positive charge. Now due to electric dipole, it is positive and negative charge. Due to this positive charge, electric field lines are from positive to negative. So field lines are stronger towards this side right now, and also field lines are stronger towards this negative of left of this negative charge. So what happens? Equipotential surface are very close. Now these are very close. Here this side close to each other and this side far away from each other. So these are equipotential surface for different combination, right? Next, after this one, electric potential energy of a system of 2 and 3 point charges. Suppose there are two charges in a system, then total potential due to these two charges in a system is given by U equal to 1 by 4 pi epsilon Q1 Q2 by R12. R12 is distance between these two charges. Now how you find this formula? For to derive this one, first suppose that Q1 charge is placed at infinity. Now the amount of work done in moving this test charge Q1 to this point, suppose A point, is what? 0, because no electric field is present at this point. Now next you assume that this Q2 charge is at infinity. Now the amount of work in moving this test charge from this to infinity to this B point. Now here already electric field is present. Due to this electric field, electric potential at point B is there. So work done you have to find in moving this test charge from infinity to point B. Now total work done, you just add these two. This gives you total potential energy of a system of these two charges Q1 and Q2. You must remember this formula. In the same way, already two charges are present. You then again move third charge from infinity to a particular point. Suppose at this point C, right now, here A, here B, two charges already present. Total work done you know. Now again third charge Q3 is placed at infinity, moving this charge from this to point C. So total work done you have found. This total work done is total potential in a system of three charges given by 1 by 4 pi epsilon naught Q1 Q2 by R12 R2 distance between Q1 and Q2 plus Q2 Q3 by R23 distance between these two charges, and Q3 Q1 by R3 distance between 1 and 3. So these are electrostatic potential energy of system of 2 and 3 point charges. Next, potential energy of a dipole in uniform electric field. What happens when dipole is placed in a uniform electric field? It experiences some torque, and that torque is given by tau equal to Pe sine theta. Now this torque tends to rotate the dipole direction of electric field. Suppose you want to rotate this dipole from theta 0 to theta 1. Then amount of work in rotating dipole from theta 0 to theta 1 is given by integration of tau d theta. Then after this you get W equal to Pe cos theta 0 minus cos theta 1. This work done rotating dipole from position of 0 potential energy. 0 potential is 90 degree angle. So you put theta 0 equal to 90 degree to theta angle. Theta we put theta 1 equal to theta. You get W equal to Pe cos pi by 2 minus cos theta, and equal to minus Pe cos theta. Cos 90 is 0. So this work done is stored as potential energy U in the dipole. The potential of electric dipole in a uniform electric field is given by U equal to minus Pe cos theta. You must remember this formula. And when theta is 0, potential energy is minus P. It is called a stable equilibrium. When theta is 180 degree, it is plus Pe. It is called unstable equilibrium. When theta is 90 degree, potential energy is 0. Right? Hope it's clear to all of you. Next, electrostatics of conductor. These are those substances which allow large-scale physical movement of electric charges through them under an external electric field, and they contain large number of free electrons. There are some electrostatic properties of a conductor. Net electrostatic field is zero in the interior of a conductor. Inside the conductor, suppose this conductor is placed in a uniform electric field. Now, due to this electric field, there is some internal electric field exists inside the conductor which is opposite to that of this external electric field, and both are in opposite direction. Net electric field is zero inside the conductor. Now according to Gauss theorem, net electric field is zero, then net charge is also zero. Right now these two are very important. Net charge is zero inside the conductor, and electric field is zero in the interior of the conductor. Now where does this extra charge resides? That extra charge resides on the surface of the conductor. They always resides on the surface, and due to this charge on the surface of the conductor, electric field is present outside the conductor, and that electric field outside the conductor is normal to the surface. Potential is constant within and on the surface of a conductor. Potential is always constant inside the conductor and outside the conductor. Next, at the surface of a charged conductor, electric field is directly proportional to surface charge density. It is given by E equal to sigma by epsilon naught. Electric field is zero in the cavity of a hollow conductor. Inside the hollow conductor, it means inside the conductor electric field is zero. So in the cavity of a hollow conductor, electric field is zero. Okay, hope it's clear to all of you. Next one is electrostatic shielding. Electrostatic shielding is nothing but that phenomena is used that electric field inside the conductor is zero. So if you want to free any region from electric field, you just put inside the conductor. The phenomena of making a region free from electric field by surrounding with the conducting sheet, because in the conductor electric field is zero. So this phenomena is called electrostatic shielding. It is a method of shielding or protecting a particular region or space of any sensitive building instrument from the effect of external field produced by an electric charge. For example, an instrument used to measure high voltage, that is CRO, cathodic oscilloscope, is kept inside a hollow conductor or case called Faraday case, where electric field is zero, so that it can be saved from the electrical circuits, right? Next is dielectrics and polarization of a dielectric. Now, what is dielectric? Dielectric is a substance which does not allow the flow of charge through it, but it permits them to exert electrostatic force on one another. Now, what happens when dielectric is placed in a uniform electric field and conductor is placed in a uniform electric? This diagram is for conductor, this diagram is for dielectric. Inside dielectric, there is no free charges. It is like an insulator. They can be easily polarized when electric field is applied. Charges are separated when electric field is applied across this dielectric. Now, polar dielectrics, there are two types of dielectric. Polar dielectrics are those which are made up of polar molecules. Non-polar dielectrics are those which are made up of non-polar molecules. Now, when this conductor is placed in a uniform electric field, inside this internal electric field exists which are opposite to the external electric field, and net electric field is zero inside a conductor. But what happens when this dielectric is placed in a uniform electric field? Inside a dielectric, electrons are not freely moved. They move, but this internal field is not always equal to the external field, and so net field is not equal to zero, right? So that's the extent to which a dielectric is polarized, described by a quantity P called polarization. So how much this net electric field due to this, it means the dielectric is polarized. Some charges are separated due to this external electric field, but net electric field is non-zero. It reduces the net electric field, right? So the extent to which this dielectric reduces the field or polarized is called polarization. How you define this polarization? Polarization is defined as the electric dipole moment per unit volume. This P is dipole moment per unit volume. It has same direction as the molecular dipole moment. Also, this polarization is directly proportional to E. Greater the applied electric field, greater is the polarization, greater is the molecules polarized, and this P equal to xi EE, and this is called susceptibility, electric susceptibility. Must remember this formula also. Now, after this, dielectric constant. Now, when you place the dielectric in a uniform electric field, it reduces, suppose this field is from, this is negative, field is from this positive to negative, and place a dielectric between these fields. What happens? Charge is separated, negative charge comes to this side, positive charge this side, and internal flux exists in this direction. Now it is opposite to that of the external field, but it is not equal to this one. So net field is E0 minus EI, which is not equal to 0. It is called E reduce. So reduces the electric field when this dielectric placed in a uniform electric field. So how much it reduces the electric field, that is represented by a quantity called dielectric constant. It is equal to E naught by E net. E naught is external electric field, E net is reduced electric field. It is given by E naught minus EI, right? And in terms of capacitance, this dielectric constant K equal to C by C naught, capacitance with dielectric between the plates, and this C naught is capacitance with vacuum between the plates. It means when there is no dielectric between the plates, dielectric is there is free space between the plates. So that is C naught. So this dielectric constant is C by C naught equal to E naught by E net. You must remember this formula for dielectric constant, right? After this, next is capacitor and capacitance. What do you mean by this capacitor? Capacitor is arrangement of two conductors separated by an insulating medium that is used to store electric charge and electric energy. What is the use of capacitor? It is made up of two conducting plates separated by insulating medium of free space, and that is used to store electric charges. It consists of two conductors, right, separated by some distance. The space between the conductors may be filled or with an insulating material known as dielectric. Now, how much it stores the charge, that is given by a quantity called capacitance. The ability of the capacitor to store charge is known as capacitance, right? Okay. The charge required to supply to either conductor of a capacitor to increase the potential difference between the two conductors by unit amount is called capacitance. C equal to Q by V. Capacitance is given by this one. SI unit of capacitance is farad. The capacitance of a capacitor is said to be 1 farad if 1 coulomb of charge is transferred from one plate to another on applying a potential difference of 1 volt between the two plates. Now 1 farad equal to 1 coulomb by 1 volt, and 1 picofarad is 10 to minus 12 farad. So hope it's clear what do you mean by capacitor. It is the arrangement of two conductors separated by some medium, right? And the main purpose of this capacitor is to store charge. How much is the ability to store charge is called capacitance. Then next, combination of capacitors. There are two combinations, series and parallel. In series combination, capacitors are connected when second plate of a capacitor is connected to the first plate of the next capacitor. Suppose there are two capacitors. Now second plate of this first capacitor is connected to the first plate of the second capacitor. These are called series combination. In series combination, the total charge across this arrangement will remain the same. Total charge does not change. It remains the same. Only the total potential drop is sum of potential drop across each capacitor. So total potential V is given a potential drop of first capacitor is V1, second is V2. So total potential is Q by C1 plus Q by C2, and Q, Q equal to CV. So in case of series combination, total capacitance is given by 1 by C equal to 1 by C1 plus 1 by C2. In case of a number of capacitors, 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus dash dash dash. So you must remember those two points. The charge across the capacitor will remain same. Total potential drop is sum of potential drop across each capacitor, and inverse of total capacitance is sum of inverse of individual capacitor. Next, parallel combination. Here in parallel combination, the first and second plate of a capacitor is connected to the first and second plate of the next capacitor. Suppose there are two capacitors. The first plate of these two are connected to one point, and second plate of these two are connected to one point. This arrangement is called parallel combination. In parallel combination, the potential across the arrangement will remain same. In case of parallel combination, potential remains same. Total charge is sum of charge due to individual charge across each capacitor. It means Q equal to Q1 plus Q2, and Q CV. So Q1 is C1 V1, Q2 is C2 V2. In this way you get C equal to C1 plus C2, and for n number of arrangements, C equal to Cn plus C2 plus dash dash dash. So 3 points you note down. Potential across this arrangement will remain the same. Total charge is sum of individual charge across each capacitor. Capacitor is sum of individual capacitors. Now one or two last. Now next, capacitance of a parallel plate capacitor. There are different types of capacitor. We are going to discuss only parallel plate capacitor, right? In case of parallel plate capacitor, what is the value of capacitor? It means what is the ability to store charge. So suppose there is an arrangement of two parallel plates are there. There is a separation between these two plates, and V is the Q is the charge on these plates, and V is voltage. So capacitance of a parallel plate capacitor is given by C naught equal to A epsilon naught by D. where A is area of the plate, D is separation between the plates, epsilon naught is permittivity of free space, right? And one more formula, capacitance of a spherical conductor. You must remember this one also, C equal to 4 pi epsilon naught R. This is the capacitance of a spherical conductor, where R is radius of conductor, and Earth is also a sphere. So the capacitance of Earth, you can easily count. Formula you have to use, C equal to 4 pi epsilon naught R, where R is the radius of Earth. So with the help of this radius of Earth, you can easily calculate the capacitance of Earth also. Now last one is capacitance of a capacitor with dielectric slab. Now what happens when dielectric slab is placed between the plates of a capacitor? You know now, if there is a free space, then capacitance is given by C naught equal to A epsilon naught by D. But if dielectric is placed between the plates, then what is the value of this capacitance? You know, when dielectric is placed, it reduces the electric field. External electric field is E naught from plus to minus, right? The positive to negative. But if you place this dielectric in between these two plates having thickness T, then it reduces the field E dash. So you have to find total potential. Now D is the distance between the two plates and T is thickness of the plate. So total potential is a scalar quantity. This and distance T, electric field E exists, and D minus T, this distance are D minus T, electric field E not exists. So you calculate total potential. Now you know the relation of E equal to E naught by K. Dielectric constant is what? E naught by E, electric field in free space, and electric field with dielectric. So E equal to E naught by K, you put the value of E here, you get V equal to this one, and after putting these things, you get C equal to A epsilon naught by D minus T 1 minus 1 by K. This is the capacitance of a capacitor when dielectric having thickness T is placed between the plates, right? And the capacitance increases when you put a dielectric between the plates. You must note this one, capacitance increases when dielectric increases between the plates. If dielectric is absent, then T equal to 0, C equal to A epsilon naught by D. This is the capacitance when dielectric is absent. It means between the plates free space is there, vacuum is there. If dielectric fills entire space, it means T equal to D, then this C equal to K C naught. It means when dielectric is placed, capacitance increases K times capacitance in free space. So capacitance increases when dielectric is introduced between the plates. This point is very, very important. And then one more last topic is the energy is stored in a capacitor. Energy is stored in the capacitor when work is done to move a positive charge from negative conductor towards the positive conductor against this repulsive force. If you want to move a positive charge from this negative plate to this positive plate, then against this repulsive force, and that work is stored in the capacitor in the form of energy, right? And that energy is given by this work done is stored in the form of energy in the capacitor, and this is given by Q square by 2C. So electric potential energy stored inside the capacitor is given. There are three forms. One is Q square by 2C, half Q square by 2C, half CV square, and half QV. These are three forms of energy stored in a capacitor. What is energy density? Energy is stored per unit volume in the region of electric field, denoted by small u. So small u energy is stored per unit volume. Energy stored is half CV square. Right now you put half CV square. Volume is what? Area into distance. A is the area of the plate, D is distance in the plates, and E equal to VD. After putting these values, you get energy density equal to half epsilon naught E square. So capacitance. Hope you like this quick revision series. After this chapter, which chapter you want, you must write in the comment box. And students, keep revising and stay tuned with this channel. Thank you.